Hello everyone, this is project 2219 titled Computational Fluid Dynamics with FEniCSx. My name is Konstantinos Kellaris and I am a 5th year undergraduate student at the National Technical University of Athens. This project was carried out at the University of Luxembourg and my mentor is Krishnasamy. This project's scope is to perform computational fluid dynamics simulations using the FEniCSx software platform. Computational fluid dynamics, or CFD, uses applied mathematics and computers to numerically approximate fluid flows. A great range of methods can be used for this purpose, and most of them require the geometry to be discretized in mesh. In general, CFD results quality depends on how small space and time discretization we can afford in our simulation, which of course depends on the available computational power. CFD evolution has been tied to the evolution of HPC. The finite element method, or FEM, was used in this project. FEM uses calculus of variations to formulate a system of linear equations. Firstly, the partial differential equations describing the problem are multiplied by a trial function and integrated through the whole domain. Then, linear combinations of polynomial functions approximate the solution in small discrete regions of the domain. The function coefficients are the values of the variables of interest in each node, for example, pressure values. Finally, all these approximations are assembled to a large linear system that includes the whole domain. FEniCSx is the newest version of the well-established Phoenix library that is now considered legacy. FEniCSx is an open-source computational platform that allows users to solve problems using the finite element method. It provides Python and C++ interfaces, taking advantage of automatic code generation. Furthermore, it supports mesh generation using GMesh, the leading open-source mesh generation software. Finally, FEniCSx is designed for parallel processing as it is developed using API. It uses a patchy linear algebra suite to solve linear systems in parallel with direct or iterative solvers, supports mesh partitioning libraries such as Parmetis and Scotch, and supports parallel I/O. The developed software can solve the Incompressible Navier Stokes equations for both present and steady-state problems. The Navier Stokes equations express the conservation of mass and momentum in viscous fluid flows. Unfortunately, no analytic solution to them exists, and they present nonlinearities. To overcome these nonlinearities, the solver uses a three-step prediction correction scheme. To validate the solver, a common benchmark was used. It is a study of the three-dimensional laminar flow around a cylinder. The cylinder lies inside a channel with an inlet and an outlet, and all the other surfaces are walls. The velocity on the walls is zero, same as the pressure gradient. This is called a non-slip boundary condition. Furthermore, at the outlet, the velocity gradient and pressure are zero. Finally, in the inflow plane, a parabolic velocity profile is specified. I investigated two cases, one with a constant velocity and one with a time-dependent profile. After defining the geometry, computational meshes were generated using a GMesh Python MPI with tetrahedral elements and then partitioned using the Parmetis library. Here I can see decomposed mesh distributed to 16 processors. 6 different setups were investigated for the first case, with 3 different meshes ranging from 60,000 to 1,000,000 cells, and 2 different sets of orders for the polynomial basis functions. Then they were evaluated by comparing the drag and lift coefficient and the pressure difference between the front and back of the cylinder with the reference values found in the literature. The simulations were run on the University of Luxembourg ARIS cluster using 64 to 360 processors. Here we can see how the relative errors change for different mesh sizes and polynomial orders. By increasing the mesh resolution, we can see that the code provides better results but with rising computational costs. Also, an increase in element order produces more accurate results but is more computationally demanding. Next, we see the velocity field at the two symmetry planes of the computational domain. Again, the behavior is according to the benchmark, and the three-dimensional nature of the flow is evident. This is also verified by the pressure contours. Next, the transient case is studied. The total simulation time is 8 seconds with a prescribed time step. The inlet profile is a function of time. 3 different cases were investigated. Case 1 and 2 both use a coarse mesh, but in case 2 the order of the basis function is increased. Then case 3 uses a more refined mesh with a lower order of basis functions. Then the time evolution of the drag and lift coefficient will be validated using the data found in the literature. Here we observe that cases 2 and 3 are close to the reference data, while case 1 lift coefficient is wrong. This is an interesting behavior, showing us that even with a coarse mass, the solution can be sufficiently approximated with an increased element order. Here we see the time evolution of the velocity field. In conclusion, the developed solver can accurately approximate steady-state and transient laminar incompressible flow in simple geometries. There are several directions the project can go. A first step would be to support meshes generated in commercial software such as ANSYS. Furthermore, an adaptive time-step method can be implemented to save computational costs. Finally, the cone can be extended to solve turbulent problems using the RANS approach. Thank you for your attention. I would be happy to answer your questions.